Space is vast, mostly empty, and entirely silent. But if you watch the celestial bodies suspended within it, you notice quickly that nothing is drifting aimlessly. They are constantly interacting, pulling toward one another across the dark. That interaction is gravity. It is a universal, attractive force that acts as the invisible architecture of the cosmos, actively bridging distances so large we measure them in light years. When you look at our own planet suspended in that exact same void, you realize we are locked into that identical physical system. Without this continuous, invisible pull holding everything together, the highly ordered universe we observe would instantly scatter into a chaotic cloud of expanding debris. This raises a practical physics question. If an object in motion naturally wants to travel in a straight line forever, why do moons and satellites constantly travel in tight circles? To keep a body moving at a constant speed in a circular path, a state called uniform circular motion, a second force must continuously pull it off its straight-line trajectory. That continuous inward pull is called centripetal force. Maintaining that perfect circle requires an exact mathematical balance. The required force depends on the object's mass, its forward speed, and the radius of the circle it's traveling. If the satellite speeds up, the inward force has to increase proportionally, or the object flies off into the vacuum. When you put those forces together, an orbit is effectively a perpetual state of falling toward a center point, but moving fast enough sideways that the object constantly misses the ground. In the 17th century, Isaac Newton realized that the mechanics keeping the moon in orbit and the mechanism pulling a heavy apple from a tree branch to the dirt were driven by the exact same physical law. He published the proof for this connection in 1687, formally establishing the math that governs gravitational attraction. It's called the universal law of gravitation. Every body attracts every other body. The larger their combined mass, the stronger the pull. Furthermore, distance weakens that attraction, inversely proportional to the distance squared. Double the distance between bodies, and the pull drops to a quarter. Gravity is a rigid, mathematically predictable rule, binding every single piece of matter in the cosmos. You can test this exact math near the Earth's surface, but it immediately presents a logical puzzle. If gravitational force depends on mass, a heavy object should fall much faster than a light one. To see why that doesn't happen, physicists look at bodies in freefall. That is a strict physical state where gravity is the absolute only force acting upon an object, completely ignoring air resistance. In a true freefall near Earth's surface, all objects accelerate downward at the exact same constant rate of 9.8 meters per second squared. A bowling ball and a feather will hit the ground simultaneously. The math perfectly accounts for this. The Earth pulls much harder on the heavier object, but that object's greater mass actively resists accelerating. The extra downward pull and the extra internal resistance perfectly cancel each other out. Understanding this requires separating two physical properties we usually treat as identical. Mass is the absolute unchanging amount of matter within an object. Weight is just a highly variable measurement. It is simply your mass multiplied by the local acceleration of gravity pulling down on you. If you are in freefall without a surface pushing back against your feet, that measurement drops to zero. Astronauts orbiting the Earth possess the exact same mass they had on the launch pad, but constantly falling around the planet makes them experience complete weightlessness. Your mass intrinsically belongs to you. Your weight is just a temporary measurement of your physical relationship with the planet you're currently near. If gravity pulls straight down on every individual atom of an object, we have to look at how irregular, asymmetrical structures ever manage to balance and stay upright on the ground. The physics shortcut for this is called the center of gravity. It is the exact average position of an object's weight distribution, a single point where we can treat the entire mass of the object as if it were concentrated right there. Physicists locate this exact point on an irregular shape by suspending the object from a few different angles and dropping vertical lines straight down from the points of suspension. Where those vertical lines intersect is the center of gravity. An object remains standing only as long as a vertical line drawn straight down from its center of gravity falls securely inside the physical footprint of its base. The Leaning Tower of Pisa stays up because, despite the severe tilt of the structure, its center of gravity still safely remains within its footprint. The second that center of gravity shifts outside the base, gravity stops acting as an anchor and becomes a rotational force, pulling the mass straight over. From the centripetal force holding a satellite in a circular orbit to the universal gravitation pulling on a galaxy, down to the free fall of an apple and the center of gravity keeping you upright, the underlying math never changes. The delicate, static balance of a human standing perfectly still on Earth is dictated by the exact same invisible tether that hurls the planets through the void.